Hello and welcome. In this video, we want to take a look at the notion of a line integral of a vector field along a curve. Okay. In the previous video, we talked about the line integral of a scalar function, and now we're going to be doing a vector field. But actually what we're going to be doing is we're going to be taking this vector field and creating a scalar function to do a line integral of. Okay. So I have here drawn a random vector field with a random curve. And sort of the main application you should be thinking of here is work, right? That is, work is force dotted with displacement. So if you have an object and you move it so far in a particular direction, the force that is required to move it in that direction times the distance it moves is the work done. Okay. Now, I say times, I say dot product. The thing is, if you think of force as a vector and displacement as a vector, then the only part of the force that matters is the part of the force that is in the direction of the motion. And that's where the dot product comes in. Okay. So what we're thinking of here is imagine this blue vector field is say a force field, it's gravity or it's electromagnetic or something of that sort. That is, at any point you can tell how much force is being applied to you. And then think of like a roller coaster, something that's going to be stuck to this track, right? That it's going to move along that track. Even if the force field, like here, right, the force field is trying to push it off the track, but it won't come off the track. Okay, so I'm picturing this object starting here at this point. Hang on here, let me get. So I'm starting here at this point, headed in this direction, right? Because that's the tangent vector at that point. And then I move along the curve, right? And at every point, the force field is either pushing me to continue on in the same direction, or maybe like out here, yeah, I'm moving in this direction, but the force field is almost perpendicular, so it's hardly pushing at all. But then in other places like here, the motion is in that direction, but the force field is pushing me backwards. So it would be doing negative work at that point. And the question is, if you move from the starting point to the ending point, how much total work is done? Well, the total work is the sum of all the little bits of work. So what we're going to do is add up all those little bits of work all the way around. And to get that little bit of work, you need essentially force dotted with displacement, right? That sometimes we write it like this. But from the point of view of the curves that we have here, the curves in the force field, if we have that curve being described in terms of, let me scroll down a little bit and get underneath this thing. So if we have the curve being described parametrically, and I'm just in 2D here, so this is x of t, y of t, right? Then the derivative vector, we saw back in Calc 3, the derivative, x prime of t, y prime of t, is the tangent vector, right? That vector here would be r prime. Now, I don't want to just dot the force field. I don't want to say, hey, force dotted with r prime, because that's not going to be the right thing. That's not going to be the component in the direction. Well, it's not going to be the component of the force in the direction here, because this would need to be a unit vector. That if I divide this by the length of r prime, then I would have the force dotted with a unit vector in that direction, and I would be getting precisely the component of f in the direction of that unit tangent vector. So the line integral we're going to set up is the line integral over the curve of the force dotted with the tangent vector, the unit tangent vector, ds, right? this dot product here is going to be creating a scalar function, and we're going to do the line integral of that scalar function. And remember from the previous video, the scalar, the line integral of a scalar function is you take that function and you multiply it by ds, a little bit of arc length. And this makes sense from the point of view of work as well, in that we have this dot product is telling us the component of f in the direction of motion, and then we're multiplying that by a little bit of length in that direction. And force times length is work. Right? Now, let's do some calculations here, some changing this. ds is not typically how you're going to do the integral because the curve isn't parameterized in terms of s, it's parameterized in terms of t. Now you could reparameterize, but it's usually easier to just get it in terms of t, little t. So I'm going to note that this then is going to be equal to ds. So this is going to be f. It's always evaluated at r. And t, remember, we calculated as r prime. That's a vector divided by the length of r prime. But then ds is the speed dt, right? So it's the length of r prime. Oops, that should be that. dt. And this is a dot product. Notice the r primes are going to cancel out, and this could look like this. This is f. There's always it's evaluated at xy, but xy is on the curve, so it's this, and I'm not going to write it in every time. So this is f dotted with r prime dt, because the r prime of t's, the lengths there cancel out. Now, r prime of t dt is quite often just written as dr. So this is the integral over c, over c, over c, f. This is just dr, with that being a vector r. This is not uncommon, right? That if you had something, remember back all the way to Calc 1 even, if you have y as some function of x, then we would say dy is the derivative f prime times dx. Right? And so that's what I'm looking at here, or even this could be written as dy equals dy dx times dx, whatever. And so this r prime dt, that's dr dt dt, and so I'm just thinking of that as dr. And of course that's a vector function because r is describing a parametric curve. Right? So when you see these vector field line integrals, we first of all think of it like that, but it is very common that it's just written like this, f dotted with dr. It means exactly the same thing because the TDS is really the same as dr. Okay. Now, there's another way that we view this as well, in that if you have f, if you think of f as, let's say, p comma q, where p and q are just the functions of x and y that give you the first component and the second component of that. We could be doing this in R3 as well, and then there would be a comma r, there'd be a third. Actually, they use capital R. It's unfortunate because we use lowercase r for the curve and capital R for the third component of the vector field, but anyway. If this is like this, then what we're seeing here is that integral is this dot product, PQ, dotted with, now dr is dx dt comma dy dt dt. So this is dx dt dy dt dt. And so what I get is, Well, you can even think of the dt as being distributed in here and canceling out, and I get the integral of p dx plus q dy, and in 3D this would look like the integral of p dx plus q dy plus r dz. And this is also another way of saying the same thing. That is, I'm taking the line integral of this vector function over this curve, where the dx is coming from the derivative of x in the parameterization of the curve. The dy is coming from the derivative of y, right? So again, dx is dx dt times dt, and dy is dy dt times dt. I remember first learning this, and this form right here just, it felt really strange to me. It's like, am I integrating with respect to x, or am I integrating with respect to y? And it's like, no, you're integrating with respect to t. Right, that all of this is going to be converted into t's in the end. And whether you do it from the original f dotted with capital T ds, or whether you do it at this stage here, or whether you do it at this stage here, you're talking an integral dt, where t runs from whatever the beginning value is to the ending value to get you all the way along your curve, right? Let's do an example. So I've got one of my favorite vector fields here. This is f of xy is minus y comma x. That's just essentially circular motion around the origin. It's circular. If you had a solid rotating, right? That's what the velocity field would be, right? The center doesn't move at all, and things that are far away are rotating faster than the things close in, because they're going to get around in the same amount of time, but they have to travel a bigger distance. So anyway, this is just minus y comma x. That's my vector field. And my curve, I'm going to do a closed circle. I didn't say here, but t is going to be between 0 and 2 pi. So at t equals 0, I'm out here at the point 3, 0. And then I rotate around in a counterclockwise fashion, and this will get me around that curve once from t equals 0 to t equals 2 pi. Okay, and before I even start, I kind of look and say, am I expecting a positive, a negative? You know, what kind of line integral do I think I'm going to get? Well, the thing I'm doing is at every point I'm looking at the unit tangent vector and dotting it with the vector field at that point. And the thing about dot products is, geometrically, you can see if the two vectors are pointing in essentially the same direction, or the angle between them is less than pi over 2, then the dot product's positive. Right? If the vectors are perpendicular to each other, the dot product's 0, and if the angle between them is bigger than pi over 2, you know, between pi over 2 and pi, then that dot product is going to be negative. So I can see on this whole right-hand side of this circle, the unit tangent vector and the vector field are pointing in essentially the same direction. At least the angle between them is small, and so I'm going to be getting positive contributions to this line integral along that side. But then I get to in about here, and the unit tangent vector is kind of perpendicular to that vector field, so that's a 0. And in through the middle here, I'm definitely fighting against it, because like right here, for instance, this vector field is pointing directly up, but the direction of motion is directly down. So that is definitely contributing negative. But it looks to me like there's not as much negative. Like the negative seems to only go from, you know, here down around to there. And they're very short vector field vectors in here, where all this positive stuff has bigger or longer vectors. So I'm expecting a net positive result. So let's see how this works. So the line integral over C of f, back up here. Line integral over C of f dotted with t ds, which I could write as the integral over C of f dotted with dr. These are all vectors here. Or I could write it as the integral over C of p dx plus q dy, right? All of those mean the same thing. But in all of them, I'm going to need to know what r prime is. So let me recall here that r was given as 2 plus cos t sine t, and so the derivative here, r prime, is, what's that, minus sine t cos t. Okay. So dr, let's just write this down just so, let's go here, dr is this thing times dt, right? Because this is essentially dr dt, multiply both sides by d. So this is minus sine of t dt, cosine of t dt. And this part right here is the dx, and this part right there is the dy. I'm thinking in terms of all these different formulas, right? This dr is all of that stuff, but this dx is just the first component, and this dy here is just the second component of that part. So now let's do this integral. So I'm going to do the integral from 0 to 2 pi, because that's where my curve is defined. F was, what was f? Minus x comma y, right? That's what's right over here. F was minus y comma x, right? But I'm not just doing y's and x's. I'm doing y's and x's that are on the curve, right? So for each value of t, the y component is sine t. So this is sine t. And the, oh, but it's negative y. And the x component is 2 plus cos t. So that part is the f, right? And now I'm going to dot this with dr, which is minus sine t dt, cos t dt, which gives me the integral from 0 to 2 pi. Doing this dot product here. The dt's, you can put them in there, or you can just say, let's just put them out at the end, right? So doing the dot product, minus sine t times minus sine t is sine squared t. And the 2 plus cos t times cos t is 2 cos t plus cos squared t. And then I got a dt out on the end. And then, what do I see? Sine squared t plus cosine squared t is 1, so I'm integrating 1 plus 2 cos t dt from 0 to pi, which would be t plus 2 sine t, evaluated between 0 and 2 pi, which would be 2 pi plus sine of 2 pi is 0, and minus what I get when I plug a 0 in, which would be 0 plus 0, for a grand total of 2 pi. So that line integral was 2 pi. Essentially, if this was a force field, the work done in moving from the starting point to the ending point, the total work done would be 2 pi. I didn't give labels, you know, is it foot pounds, is it Newton meters, or whatever. It's some amount of work, right? But that's the notion of the line integral of a vector function. You are taking, sorry, it's the line integral vector function along a curve. It's taking the part of the vector field that's parallel to the curve, multiplying that by a little bit of arc length, and adding it all up. Okay. We're also going to have the notion of the line integral of a vector field across a curve, where you're not looking at the tangential part of it, you're looking at the normal part of it. But that's for another video.